Um, Hi everyone. So I think we can go ahead and get started. We have like 20-ish people. Some people should come in a little bit, but we'll just get started. So so originally a lot of you guys, like I'm sure you guys saw that we were only gonna do 6 weeks, but since we felt that it would be a lot better if we had 2 more weeks in at the end, especially for you guys to do projects, because we think that you guys doing projects will be a very good experience. So what we want to do is we want to spend the next 1 to 2 more weeks learning stuff and actually learning how to code stuff. And then after that, we'll do project sessions where you guys will just like, we can do things where like breakout rooms, you guys can all work together and you can create groups and stuff and create projects and we can help you guys. We think that's like a really good, that'll be a really good experience for everyone, especially to get hands-on learning. So for today, we're going to learn about CNNs, and that's a convolutional neural network. And so first we'll obviously go over like the theory behind it, and then after that, so Viraj will do that, and then after that, I'll go ahead and we can do some code that you guys should follow along. And so we'd really appreciate if you guys copy that with us. And for anyone that copied last week's code, or any of the code you have so far, please upload it to the GitHub, because that really helps us understand how much you guys are like really being able to copy down, how much you guys are really understanding in terms of code. So if you guys have any files, anything that you want to that you have like coded during the lessons or on your own time, please upload to GitHub. But other than that, I think we can get started.
Okay, I'll go ahead and screen share now then. Ian, can you turn on screen share?
Yeah. There you go ahead.
Okay, so up until now, you guys have been learning about what is a traditional neural network, right? You guys have been learning what they do, how they're used, and what they're good for. And up to a certain point, they're really helpful. But for some specialized tasks like image recognition, you have to use a different type of layer. And one of the most popular types is called a convolutional neural network, CNN, like Ian said. And these are mainly used for image recognition and detecting patterns and classifying them and basically everything along those lines. And they have a lot of their own kind of advantages and disadvantages. And today, as Ian said, I'm going to show you how we build one of those, and then he's going to show you how to code them. So let's just get started with analyzing why we need a CNN. Why can't we just use a traditional neural network instead of a CNN? And hypothetically, what people originally did is they did use a traditional neural network for image recognition and everything along those lines. But the problem is, a traditional neural network will basically take this grid here and then convert it into an array like that. And then one by one, you'd feed each of these inputs into your neural network, right? But the problem with that is if you're analyzing an image, you need to be able to tell the difference between this one up here and like this two in the center, right? Because depending on what the image is, that'll be really helpful for figuring out a pattern that you want to establish in your images, right? But if you just convert this into a neural network, you can't tell the difference between a 1 over here and a 2 over here, right? And so people realized that they needed a better way to determine the difference between these. And to do that, they came up with the CNN. And so a CNN, that's basically its biggest advantage. It's able to successfully capture these spatial dependencies by applying filters, which we'll learn about. But basically, it's able to tell the difference in space, in positional orientation. And a CNN, it'll usually have 3 main layers. So you obviously have the input, and then this one, the convolution layer, is where you determine exactly what your feature is. You need to determine the pattern that you want to extract out of your images, right? And then after you're able to extract that feature, at that point, it's going to be actually really, it's going to be a lot of data that your system needs to store. And so you use a pooling layer to make your system more efficient. And after you make your system more efficient, at this point, you have a bunch of features that you extracted from the data set that you're able to differentiate between. And after you're able to differentiate between these layers, between these features, you feed that into a traditional neural network, which we call, in this case, the fully connected layer. And the fully connected layer is basically able to take each of these features, each of these patterns, like a nose or a paw or something, and assign importance to them. So obviously you're not going to assign the same level of importance to like a strand of hair as you would to a nose if you're doing a cat and dog CNN, right? And so the fully connected layer basically lets you put weights on those. And just to go over that again, the convolutional, we have an input, we have a convolutional layer, which lets you identify the features in, identify specific features in your image. You have the pooling layer, which will make your system a lot more efficient. And you have a fully connected layer that assigns importance to each of these features. Does everyone get that? Any questions? Cool. So for what we're doing today, we're going to, as I've said, we're going to do a CNN that's able to tell the difference between a cat and a dog. And as an example, this is what our model structure will look like. For each convolutional layer, you need to have one pooling layer. And so the model that you guys will be building, it'll have one convolutional, one pooling, and then you'll repeat that 3 times for 3 layers, and then you'll use a fully connected layer to basically assign weights to each of those. And so let's just go over each of these layers in detail. And so the convolutional layer is definitely the most important layer. The convolutional layer is, again, the one that will extract a feature from the input image. And this convolutional layer is really important because it'll preserve the relationship between pixels. Up here, it'll be able to tell the difference, tell the relationship between this 1 here and this 4. And the convolutional layer will do that using something called a filter. And convolution will basically take your filter, it'll take your image, and it'll put them together and multiply them to create a new image matrix. So a filter, to clarify, is basically a matrix of learnable weights that you gradually train through backpropagation, which is the same as a traditional neural network that we've talked about in a previous class. And a filter will basically go through this entire image and map each of these sections one by one, and it'll learn each of these portions. And a filter is really useful because, again, it's able to detect features. So for example, if you want to look for like an edge in an image, a feature will be the key that will determine that. If you're looking for a paw, a feature will be able to tell that. And by gradually improving the filter through backpropagation, you're able to increase the accuracy of how it can detect these images. And let's just go through an example because I know that's very theoretical right now. So imagine you have an image matrix here, right? So this is just an image, a 5 by 5 pixel image of, and we're going to call some of them 1 and some of them 0 here, right? And here you have a filter matrix, and a filter matrix in this case will just be a 3 by 3 that will go through this image. And I'm not sure how many of you guys have taken algebra, but when you go to algebra, you learn about how you can multiply these matrices together. And so you're going to put these two together. And as you can see in this GIF, the filter, let me just wait for it. Okay, so the filter will start in one position and it'll gradually go over into each position. It'll basically overlay it, right? And at each position where it will overlay it, it'll multiply the filter with the matrix at that level, and it'll feed the output of that to another layer, another matrix, which we'll call a feature map. So if you guys understand this diagram right here, the filter is basically going to these 3 rows. This proportion of the matrix, and it's multiplying 1 by 1, 0 by 1, and it's doing that, and it's basically feeding the output to this purple matrix, which we'll call a feature map. And so basically, as I said, the filter is basically able to map each portion of the image to this feature map. And so obviously the filter is the most important part because you're able to isolate these features. But you have one more portion in this layer called a stride. And a stride basically tells you how far the image will move over. And so I'm not sure why the image isn't working, but imagine you had a filter right here, and right now you're moving one layer by one, right? One pixel over to the right every time. But imagine you were moving 2 pixels. So it starts here, and then it would move over to the middle here. It'll move over 2 pixels instead of 1. And depending on that, that'll have a really noticeable impact on how your image may look. And the last thing I want to go over for the convolutional layer is padding. And with padding, you sometimes, if you have a feature layer, it's not going to fit the image perfectly, right? And so you need to make the image and the feature compatible with each other. And you do that in 2 ways. Either first, you're going to fill the image up with a lot of zeros, and we call that zero padding. And if you just add that and you kind of change the dimensions of the image, you'll basically make it compatible. And the other option is to basically crop the image into a shape where the filter can actually work. Do you guys understand the importance of features in a convolutional layer? Do you have any questions?
No.
Good. Okay, so the convolutional layer. At this point, we will basically have feature maps that can tell. We have feature maps that will basically be able to tell each of these features, like a nose or a paw or a tail or something, right? But because images take up a lot of space and you have a lot of inputs for them, you need to usually make this more efficient so your computer can process it a lot better. And you do that using a pooling layer. And a pooling layer, again, will basically let you decrease the computational strain on your computer. And it does this, a pooling layer has 2 ways it can do this. Either it'll have a max pooling layer or an average pooling layer. In general, we tend to use a max pooling layer a lot more, because it's a lot more efficient and it works a lot better for most types of data sets. And the difference between them is that a max pooling layer will basically take it'll return the maximum value from the image. It'll return, for example, if we were up here, if you have an entire matrix of this, it'll just return like a 1. Let me just, sorry, the images somehow are not showing up. But if you guys go to the notebook after class, you'll be able to see how the images work. But basically, the max pooling layer will take the it'll take the maximum value from the image being covered by the filter. But opposed to this, the average pooling will just take the average of all the values from the image. And in general, when we're looking for features, we want to always find the most dominant one, right? We want to isolate the biggest and most important part of the layer. And for that, we would use max pooling, because max pooling will let you take out all the noise, all the extra stuff, and leave you only with what you need. It'll give you only the feature. It won't have all this random noise in the background, right? And pooling layers, because you're taking out all that noise, it'll make the entire system more efficient. Do you guys understand? Cool. So that was pooling layers. And at this point, we have feature maps that are just completely open. That are just completely clean. They don't have any noise there. They just have the isolated feature, right? And now that we have that, we can feed that into a fully connected layer. And a fully connected layer, as I mentioned earlier, it's basically a normal neural network layer. Everything that you guys learned about in the previous classes, that is a fully connected layer. And the fully connected layer will translate the feature maps that you came up with. It'll translate that into a one-dimensional array, a 1 by whatever array, and it will assign importance to each of these features. So it'll say that the feature of a tail is more important than the feature of an ear or something, right? And the fully connected layer will basically let you determine the nonlinear relationships between all these features, and again, assign importance to them. And so at this point, you're basically done. You took if we go up back here to how it works, you took your image, you put it into a convolutional layer, and you isolated the specific features from each of these layers. Then you made it more efficient, and then you assigned importance to each of these. And From here, now that you assigned importance, you have, in our case, you'll have two outputs. You'll have either 0 for like a cat or 1 for a dog. And uh, and at this point, you can basically predict it. And it's actually really simple. That is everything you need. Do you guys have any questions about anything I went over?
No, not really.
Okay, good. And do you want to take over and have them actually code this?
Yeah. So let's
Okay.
go ahead and let's get started. So everyone should open up a notebook right now, and then we can just it'll be really easy code to copy. So why don't you guys open up a notebook, and I'll just give everyone a second to do that. Okay, so I'm gonna zoom in just a little bit for you guys. So we're gonna download this this code. We're gonna download a zip, and a zip file just has all the images that we need. So if you guys can, I don't have a chat unfortunately, so I can't really give this code to you. But if you guys can you please run this word for word? I'll try to put it in the Slack, but you just try to read it and just copy it. But let me go ahead and put it in the Slack for you guys. So just copy that and then just run it. So when you run it, it should just start like downloading the zip, and then it shows up right here. So I'll give you guys like 5 minutes, like 2-3 minutes to go ahead and get that ready. You don't have to worry about how it works. It just like downloads the images for you. It's not important to learn how to code. So is everyone following along? I guess, like, is everyone have their own notebook open? Because if once you guys are done, we would really appreciate if you uploaded to GitHub, just so we can really kind of follow along on what's going on. Okay, so then I'll wait for you guys. But in the meantime, basically we're gonna load the data from Kaggle, and the goal right now, we're gonna build a CNN that is going to classify an image as a dog or a cat, right? So this is how we're getting our images. So then we have to unzip this file. So what you want to do is you want to call import OS. That's just for getting files. And then you can do import zip file, which just unzips the image for us. So when we do that, we can get, and these lines just copy it. So why don't you guys just go ahead and copy this. And then when I run this, it will unzip the file for me, and I have all my images here. So while you guys do that, let me quickly explain what these images do. So quickly, please copy this line of code and this cell and this cell, really important. But while I do that, I can quickly show you guys what this looks like. So here we have our entire folder of all our images, right? And then we have our train sets. Whoops, let me close this real quick. We have our train set, and we have our validation set. So in each of these, we have two folders. We have a folder for cats, and we have a folder for dogs. And that is basically how we tell our model that it's like a cat or a dog, right? Because it's like, you know which folder it's from. So why don't we take a look at these images? So let me, yeah, so right here you can see that it's a cat. And this is not a great picture, but with this specific task, all the images look very different. And that's why it's a good task to learn, because since all the images don't really look the same, it's really hard for the classifier to make a really good like a really good model, right? Because all these cats look really, really different. So that's how you make a really good one. So those are the cats look like. And then let me quickly show you what the dogs look like. And obviously, like, to you, you can tell like what is different about like a cat and a dog. Like, you just learned that. Everyone knows that, right? But for a model, it's a lot different because it doesn't actually have a real brain. It doesn't really know things. You have to teach it by giving it the images. So here's one picture of a dog. Here's another one. So these are what the images look like. So I'm gonna assume everyone got this down, and we're gonna like make sure that everyone's doing it by like, we're gonna check your guys' GitHub, and we're gonna hope that you guys have it all. If not, well, I mean, if you guys weren't able to upload it, just email us, or not email, just message me on Slack, or if anything that you like didn't understand, please just message us on Slack. And if you guys didn't, we'll probably text you guys and ask you about it and make sure you guys are all keeping up. But so now let's define the directories, right? Basically, the data set contains 3 subsets: a training set, which is what we're going to train our model on. It has 1,000 samples of each class. So basically 1,000 images of cats, 1,000 images of dogs, and then a validation set, which 500 images of each class, and a test set with 500 images of each class. So that means total we have 4,000 images. And here's what it looks like. So we have our big folder, we have test, train, all that, right? So now what we can do is we're going to create we're going to do some file work, and you don't have to really worry about too much about how this works. Basically, it's just going to create different directories for us just to access our images. So just copy this.
Can you paste this cell in the Slack?
This cell right here, or the download cells?
The base bear cell.
Sure. Yeah. Or actually, why don't you guys do this? Why don't you open up the GitHub and then go to the cat dog CNN, and you guys can just copy the code from there. It's going to be a lot easier if you just press reload until it gets ready. I'll put this in the Slack, but in the meantime, what you guys should do is you can just quickly go over to the GitHub and try to reload it. It should work after a few times. It is a little bit big, but it should work. Okay, it'll work for you guys. So just open that, and then yeah. So basically what we're doing here is we're first getting the base directory, and this is just file path stuff, right? So we're just doing the train directory is this, and we're going to create the train thing, and then we have the validation directory, and we're going to do validation. Then we have the train cats directory, and we're going to do cats, and we're going to do train dog directory, and we're splitting it up like this, right? And it's already done for us. So what we can do is we can run this, and then it'll just go really fast. And then let's see what the file names look like. So when you run this, oh, whoops, I have to do, this should be content, my bad. And then it should be, yeah. So if you run this, and then you can run this. Yeah, so now make sure you change that from TMP to content, because content is how Google Colab works. This is called the content area. And then basically what we're doing here is we're just looking at the file names. You don't have to copy this code, but it just shows you what it looks like. So the file names are cat.700 and then .jpg. So they're all in a JPG file format. And it just kind of gives like what image number and like which class it's from. That's just how the files are named. You don't have to code this. So now what we can do is we can just quickly look at how big our training sets are. You don't have to code this either. This is just for us to explore our data. So we see that the total training cat images is 1,000. That means there's 1,000 images in here. And then the dogs, 1,000 images here. And then 500 images here and here. So that means we have two. Yeah, go ahead.
What does the cell you just posted in the Slack, what does it do?
Yeah, so that basically splits all of our directories. It basically creates this for us. Do you see how it like splits everything up into a train and validation set and then cat and dog set? Does that make sense? It's just splitting up the directories. You don't have to really worry about it. It's not too big of a deal. Does that make sense?
Yeah.
Okay, cool. So we got it, right? We all understand that there's 2,000 images to train and 1,000 images to validate. And again, training images is what our model learns from, and validation is to see how well our model is actually doing at predicting. So every epoch we run, we want to validate and see how well it's doing. So now we can quickly visualize the data. You don't have to worry about this, but what we can do is this is just for creating our plots. So it's just, we're importing matplotlib, and then what we're doing is matplotlib.image as mpimg, and then we're doing import matplotlib.pyplot as plt. You all worked with that before. So for our graph, we're just gonna output 4x4 configurations because that's easy, and then we're just doing we'll start with the index at 0. So you guys don't have to copy this because it's not the model building, but I think it's good for you guys to follow along because it just shows you what the images look like. So when we run this, so it'll take a second because it has to load all the images. But now we see that we have a bunch of different images, right? We have some dogs, we have some cats.
I have an
right,
error when I'm running that cell.
What did you say, sorry?
I have an error when I'm running that cell.
Which cell?
f equals plt.gcf, that cell.
Yeah.
says-
So you don't have to run this cell because I don't think you copied this, but you don't have to run it because it just shows you the images. It's not that big of a deal. All you have to do is code the model. So just don't worry about this part because it's just for looking at the images. I just wanted to show you guys the images.
So we can delete the matplotlib, import matplotlib cell in the fig equals plt.ge. So
Yeah,
we can
you
delete
don't
the
need this. No, you don't need this. Okay, so now I think everyone understands the task, right? The task is basically we want to classify an image as either a cat or a dog. It's that simple. And all we did so far is just split up our directories. We just like pretty much created this, and this is all we need. We just want everything in a separate file. And again, basically, and then this is just to look at our images. These are what the images look like. And you can see that they're all very different. So it's going to make our classifier task very difficult because all these images look weird. But that's not difficult for you. It's difficult for the model. And that's why you might see lower accuracy because all the images look very different. And we're going to use a very basic classifier, and very basic model. But I think all of this, everyone, like, it's pretty simple. It's just looking at images and it's just creating all these directories. So now what we can do is we're going to build our first convolutional neural network. And it's very different than, not very different, but it's different from a regular neural network, right? And I'll explain why. So first, let's just go ahead and quickly do our basic imports. Import TensorFlow STF, import Keras, and import Keras. From Keras.models, import sequential. When you run that, it'll take a second, and then basically it'll work, right? So next, what we can do is you guys should all should be copying now. Everyone should be following along now because now we're actually building our model. So as I explain this, you just keep copying, and then I'll explain each part of it. So basically, first, remember everyone remembers how we have to create a model, right? We just do model equals, and we're gonna do TensorFlow.keras.models.sequential, and then we're gonna put a parentheses first, and then we're gonna put brackets inside, and we're gonna create our actual model, and we're just gonna add all the layers we need. So first, we're gonna do tf.keras.layers.convolutional 2D. So we're gonna create a 2D convolutional layer, right? And the input size is the desired size of the image, which is 150 by 150 with 3 bytes of color. So basically, we have 150 pixels by 150 pixels. That just means like we're gonna. Do you see how all these images are kind of different size? We're gonna crop them all to be the same size. And so while you guys are copying, please be copying. I'm gonna like check if everyone's following along. Just have questions if you have any. But basically, 150 by 150. That's how we're gonna. And those are pixels, so we're gonna shrink our image. And then the 3 bytes, I don't know how many of you guys know this, but basically for every image, each pixel has a code and it has like a color code, right? So there's the RGB scale, which is red, green, and blue. And it's 255 by 255 by 255. That's how images work. And basically you assign a value for each. And that's why we have a third array, which is just for the colors. But let's look more in depth. Here we have 16, which is our input nodes. That's how many nodes we have to start, which means it's a 4x4 image, right? Because 4, then it's a 16 pixels. Then we have these 3 and 3, right? So these are basically our kernel size. And as Viraj went over in the last one, when you basically, it's basically each little convolutional feature map, right? It's a 3x3 and we're just going across and we're just going across the image, and we're using the 3x3 for this layer, right? And we're gonna use the activation function of ReLU, and that's the first layer. From the second layer, we're gonna use a max pooling layer. And what max pooling does, it basically takes whatever grid you have, and it just finds the max value inside of that. And the point of that is to find features and to basically make the task a little easier. And so again, we do tf.keras.layers.maxpooling2d, and we're gonna give parentheses 2, 2. And that just means our kernel is a 2x2, right? So we have a 2x2 grid that goes across. And that's for max pooling, which basically finds the max value. Okay. Then we have another convolutional 2D layer. It's very similar to the last one. It's just now it's bigger because it's getting bigger each time. It's 32 nodes. and we're using a 3x3, and it's just activation function of ReLU, very similar. Another max pooling layer in between each layer. It's the same thing as before. Then one more layer, which we're doing a 64 nodes this time, and it's another 3x3, an activation function of ReLU, very similar, just doubling in size each time. And then lastly,
excuse me?
yeah.
I opened the GitHub notebook and I'm running through it. When I get to the from tensorflow.keras.preprocessing.image import image data generator image data again, that cell, it's giving an error saying that file not found, no such file directory, temp, cats and dogs, filtered train.
Yeah, so I explained this earlier. What you have to do is you have to change temp to content. Change the word temp to content. And then try that, see if it works.
Excuse me.
Yeah.
I have just a quick question.
Yeah, go ahead.
Is there a reason why you're using the activation function ReLU? Like,
yeah, so
could you use like anything else, or have to be ReLU, and why?
yeah, so the reason we use ReLU is because ReLU's been like through like research and everything, like people have done all kinds of investigations and like experiments on like which is the best activation function. And for convolutional neural networks and really most neural networks, at least at the base level, ReLU is the best one. And I can quickly show you what ReLU looks like. Let me go ahead and right. So what the function looks like is basically it's this one, right? Oh, whoops, wrong one, right here. So basically what it does, if it gets a value that's negative, it just assigns it a 0. And if it gets a 1, it's just a linear straight up y equals x. And it's just a really good basic function. Yeah, hello?
Can you post the temp to content one? Because when I'm trying to do that, it's giving more errors.
I'm not sure why, but sure. Let me see if I can upload it for you right now. Yeah, let me go ahead and do that. So you can just reload. I'll tell you when to reload the GitHub.
Okay, thanks.
Is there anyone else have any questions about our model right now? Because that's the main thing we should be focusing on. Any other questions about the model? I mean, I'm not done explaining it, but so far, like, does everyone understand how like the max pooling layers? Does anyone like have any questions about like how the max pooling and everything like that works?
I don't think so.
Okay, that's fine. So let's keep going. So basically now we're gonna flatten the results so we can feed it in, and we're just gonna do flatten, and we're just gonna do this. tf.keras.layers.flatten with the parentheses, because we're calling a function. And then we're adding a hidden layer that's inside. A hidden layer obviously again is in the middle. It's in between the input and output layer. And it's gonna have a 512 neurons, 512 nodes. And then activation function of ReLU. And again, whoever asked that, did you understand like why we use it? It's just because it's been proven as one of the best ones.
Yeah, I asked that, but I didn't even hear anything you said. The moment I asked the question, my thing crashed and I got kicked out.
Oh yeah, no problem. Let me explain again. So basically, the reason we use ReLU is because ReLU, through like research, like a lot of professors and like high level people in the industry, they've gone through and they found that ReLU is one of the best ones just because it performs really well for image classification. And really all neural networks, ReLU is a good activation function. I've never really seen anyone use anything else. And it's just proven to be good, and it's just really basic and it's really simple. It's just, yeah. Does that kind of answer your question?
Yeah, thanks.
No problem. And then, but again, those are only for input and hidden layers. For the output layer, we usually always use a sigmoid or a softmax. But for this one, we're using a sigmoid. Let's keep going. So the last layer is only.
How long does it take to train the model?
I can't remember, but hopefully you didn't go too ahead. But I'm not sure. It'll take a little bit. So, anyways, what we have is for the output, we only have one output neuron, and it's basically going to contain a value of 0 to 1, and that's our prediction, right? So for one, we have cats, and for the other is dogs, right? So that means if it's closer to a 1, we're going to get cats. And if it's closer to 0, we get dogs. So basically, if it's above 0.5, it should be a dog, or it should be a cat, sorry. And if it's below 0.5, the number that we're getting, the prediction, it should be a cat or a dog, my bad. But lastly, and then that's how we code it. We just give it a 1 neuron, and we give an activation function of sigmoid because that's an output layer. And this, everyone, I'm sure you guys all copied this by now. So hopefully you can quickly run this. And then when we run that, we've created our model. And then when we summarize it, this is what we see. We see that all these parameters that we have to code. Do you see for this one, we have about 9 million different parameters we have to change because it's such a big layer. But, and parameters are weights. So that means this training is going to take a little bit of time because there's so many different parameters that we have to adjust within our model. Let's keep going. So now we're going to compile our model. We're going to train our model using the binary cross entropy, which is basically, it's just a, what is it? It's a loss function. And since it's a binary classification problem, we're just going to use binary cross entropy. And binary means like 1 or 2, right? It's just like 2 outputs, 0 or 1. And our final activation is sigmoid. We'll use and for this one, we're going to use a learning rate of 0.001. That one, the learning rate is one of those things that you always have to test and figure out which is the best. But usually it doesn't make too big of a difference in your accuracy. This number 0.001 is going to be good enough. And during training, we want to monitor classification accuracy. So the way that we code that is first we're going to do from TensorFlow .keras.optimizers. We're going to import Atom. And from, I'm sure you guys remember, Atom is the optimizer. And the optimizer, what it does all the calculations in the background for you. It basically calculates how to adjust the weights and how to optimize your model. And we're going to use Atom. So we do model.compile and we give a couple of parameters. First, we say that the optimizer is equal to Atom and the learning rate is 0.001. Then the loss is binary cross entropy. And for metrics, all we really need is accuracy because nothing else is too important for us. So that, you guys can run this. And now here, okay, this is where it's going to get a little confusing. I would recommend just copying what I have in the GitHub. But basically what we're doing here is this is just adjusting our images so that they're ready for training. We have to actually, we basically have to convert them to arrays and numbers instead of just being a raw like JPG file. So what we're doing is we're just shifting the width by 0.2, shifting the height by 0.2, and we're just kind of zooming in and stuff. And we're kind of making it like basically very simple, right? And then we're just doing rescaling to 255. And then we're doing, basically we're doing a batch size of 32, which means we're giving 32 images at once. What else? We're using the binary class mode. Everything else is pretty straightforward. So why don't you guys take a second to copy this and then we'll see. Anyways, so I think basically we're basically just resizing the images. This isn't too important. It's not too much like something that you should understand right now, but just copy it. And then you do need to do this to run our model. So why don't we go ahead and run this? And then so now it's ready. So now we'll train. And everyone remembers how training works. It's very simple. It's just one line of code really. It's basically where you're doing model. So we're gonna do history, and history just like is the conventional name for basically, it saves all of our metrics. So for Epoch, it saves all of our accuracy and everything. So we'll do history is equal to model.fit, and we're gonna give it the train generator, which basically has all of our labels. It has all the labels, it has all the images that we need for our model to train. Then we're doing validation data is equal to validation generator. We're giving a batch size of 100. We'll do 20 epochs. We'll do 50 validation steps, which means that we'll do 50 images at a time for validation. And we'll do a verbose of 2, which just tells you how much, like, gives better updates during training. When we run this, we're gonna see that now, if you guys remember for the other models that we did in the last 2 weeks, it went a lot faster, right? But now you see that it's going a lot slower. And the reason is because one, we have 2,000 images, right? There's a lot more data that the model has to go through. But additionally, it's images, which means there's a lot more the model has to learn because images are a lot bigger and they're a lot more complex than just a number, right? So that's why this training is going to take a little bit of time. So in the meantime, what we can do is, while this trains, I'll kind of just go over what would happen after we train. But we'll go back to that in a second. So let's assume training was finished. What we would do is we would plot the accuracy, right? And everyone should get comfortable with matplotlib, because it's a really good tool for making plots, and plots are really important in machine learning and AI, because you have to like learn about how your model is progressing. So what we can do is we'll do accuracy is equal to history.history accuracy, val accuracy is equal to history.history val accuracy, loss is equal to history.history loss, and we're doing val loss is equal to history.history validation loss. And accuracy is obviously how well is our model predicting images. The validation accuracy is how well is our model predicting images on the validation set, which are images it doesn't see during training, which means that it's not learning from these images. And that gives you a good idea of how well it's actually learning new images. The loss is we're just using a basic loss function. We're just seeing what our loss was. And then we're getting also the validation loss, but those two aren't that important. So for when we plot this way, we want to get how many epochs we ran. So we just do epochs is equal to range, then the length. This is basic Python, range, length, accuracy, which basically gives us the length of this array. So we plot it, right? So we do plt.plot epochs versus accuracy. So our x is our epochs here, y is our accuracy here, and then we're also plotting the validation accuracy. We're giving it a title, and we are plotting. So as we can see, the first one is blue, I believe. So during training, our accuracy is going up and down a lot. It's not doing very consistent, and it maxed at about like 62, which is pretty terrible if we're being honest. This is a very bad model, but it's okay because it's very basic and it's good to understand. And again, the reason it's not doing very good is because one, our architecture is pretty terrible, and two, our images are very different, and this is not a great data set. But it's good for intro because it's really good to learn the basics of it. And whenever you have a basic model, you're never going to see very high accuracy. But like state-of-the-art machine learning models go up to like 95, 96, 97% accuracy. But for right now, we're going to have very low accuracy. But luckily, we can see that our validation accuracy is pretty high. It gets to about 66. And that's on images it's never seen before, which, and that being better than our training accuracy is a good sign. So now what we can do is we can do some fun stuff. Let's make a button where we can upload a data sample and predict whether or not it is a cat. Let's see if I can run this. I don't think I can run this right now because I'm training, but let's go back to the training, right? So basically, we're seeing that our first model, or our first epoch, it took about 60 seconds to complete, and it had 63 batches to go through. And that means there's a lot of images that have to go through, because in each batch, there is a lot more images, right? So it took 60, and we see that our accuracy is complete terrible. It's 50%, which is very bad. But it's only the first epoch, so it's always going to get better, right? So is anyone training right now?
Me.
So how far are you in training?
10th epoch.
Okay, nice. And what is your accuracy? What does it say?
On the 9th epoch, the accuracy is 6.275. I mean, 0.627. Yeah, 0.6275.
Right. Yeah, that makes sense. So
yeah, now it finished the 10th one. It said 0.6410.
Right. So yours is getting higher as it progresses, obviously. So for everyone, if you guys are training, is anyone else training? Is only one person really training right now? Is anyone else training? Oh, okay. Someone raised their hand. Do you want to speak up and quickly just say like how far you are? Hello? Okay, that's fine. Anyways, so that's pretty much, you have to wait for this to train. It's going to take a little bit. It'll probably take like, looks like it's going to take 20 minutes considering that it's 60 seconds. So I don't think we'll be able to finish in our time. But basically what we see is that we've plotted and we've got a decent accuracy of 66, which is not good, not great. And lastly, what you can do is you can always save your model by doing model.save, and you do cats, dogs, small to, why don't we just give this a better name? We'll do cats, dogs. And then we're saving it as an H5 file, which basically saves our model and saves all the weights, and then we can load it later for making predictions. So is there any questions? Because we do have a little bit of time. Is there any questions about anything we learned today? Anything about convolutional layers? Anything about how to create these models, because you guys should ask questions now. Does anyone have any questions? I mean, it was probably pretty confusing considering that these are all a little bit advanced topics, but we thought it'd be good to go over, especially because some of you guys, you want to make projects, and some of the projects you guys want to make might have to use images. So we want to teach you guys about convolutional neural networks.
Just a quick question.
Yeah.
I know that it's being recorded. Is it going to be uploaded to the tiny URL link? Because I want to review this maybe later.
Yeah. So so far what we have is I believe we have the week 3 and week 4 video up. The week 2 video is, we're looking for it. We're not sure exactly where it was saved, but we'll find it. We'll get it to you guys. But week 3 and week 4 are up, so you can go check that. And this will be up soon. Like probably within like a few days.
All right, thank you.
No problem. Does anyone else have any questions about the actual like model right here, about all these layers?
Can you review everything you did today?
Yeah. So I guess Viraj, do you want to quickly explain some of the summarize the theory stuff, and then I can quickly explain the code?
Sure. Yeah. So a CNN is basically used a lot for image processing. It's a lot better because you can tell relationships between pixels better than a normal neural network, which will just make it like compress it too much for us to understand. And for a CNN, what we do and what Ian just showed is that we first, we have an input, which is usually an image of some sort. Over that image, we'll basically use a filter to map, we'll use a filter to extract the features. So for example, in the cat, we would extract various parts of the cat out into the convolutional layer. That's what the convolutional layer does. It'll extract everything. And then we'll make the entire model more efficient with a pooling layer, which will basically take the maximum value from the feature map, and essentially that'll take the most important part, the dominant element in the feature map, and then using these elements that we've now extracted out of our images, we'll assign importance to them. We'll say that the cat's eye is more important than the cat's hair or something. And we'll do that in our fully connected layer, which is basically like our a traditional neural network. And if you look on Ian's screen right now, you can see that he took you through all those parts. We have a convolutional layer, a max pooling layer. You repeat that 3 times for 3 separate layers, and then you feed all of that into a fully connected normal neural network layer. And the main reason, again, why we use a CNN is because it can tell relationships and patterns between data sets, specifically for images, much better than a traditional neural network can. And Ian?
Yeah, so I guess one thing is, what kind of projects do you guys have in mind? Or is there anything that you guys want us to go over? Have any of you guys, like, I guess maybe looked on your own, looked into maybe some projects you guys can build? Because we want to, in the next 2 weeks, I guess we want to go over, we want you guys to build your own projects. So we would like, does anyone have any suggestions on what kind of, something you're interested in, and then we can kind of go over that, and then we can kind of teach you guys about.
I am making a project that can detect a mask.
Yeah, I think you told me about that. That's really cool. But I guess, is there anything else that you guys want us to teach you guys in this class? I think object detection is going to be a little more advanced than what a lot of people in this class can do. So we want to do something a little more simple. Is there any projects that anyone has in their mind that they were thinking would be cool to do? Okay, that's fine. You guys probably haven't, like, I guess, done your own research on that. So I think what you guys should do before next week is, 1, review all these convolutional layers, right? Convolutional networks. And then with that, you guys should also go over some of these data sets and some things you guys can learn about. So if you guys look at the sample data in Colab, there's a couple projects. Basically, first, there's something called the MNIST data set. And maybe you guys have heard of it, but that's like the very basic machine learning project where you take digits and you try to classify them as a certain number. That might be something you guys are interested in. but there is a lot of different things that we can do. But it does come down to what you guys want to do. So you guys should do your own research at home before our next class. Just look up online what kind of really basic machine learning projects you can do, and then come to us and we'll help you do that. So I think we are good for this week. We're good for today. Yeah, I think we're fine then. I think we'll head out, and then for next week we'll just probably maybe next week or the week after we'll start projects. But again, this class has been extended by 2 more weeks, so just to get you guys all doing projects. All right. See you guys next week then. Bye.